the first topic is that of countable and uncountable. And I over the summer, I went on a canoe trip with my brother and two brothers. And we started talking about entropy and Kolmogorov complexity and such great things. And that got me making new slides. So what I would like us to do, if you're up for it, is to cover my new slides on this topic. All right, the first bunch of slides are identical to what's recorded. I'll go over them again just to put them all together in one context. And then the new slides on random versus patterned have never been presented before. All right, you guys good? All right, so let's first think about the concept of finite and realize that finite is actually a pretty big word. Something can be pretty big and still be finite. So let's define a set S to be all little teeny Planck's constant size bits in our universe, all right? And let's count how big that set is, all right? So how big is Planck's constant? Well, it's 10 to the negative 35, which I have this great video that you might want to watch sometime, which starts off something that's about this size, and it scales down, and it scales up. So it's neat to see how big things are and small things are. And Planck's constant is really, really small. And the belief in quantum mechanics is that nothing is smaller than Planck's constants. You can't measure anything smaller than that. How big is the universe? Well,
I'm sorry, sir. Sorry, sir. Are you supposed to share this your screen or?
Oh, I am supposed to share the screen. Sorry. Thank you for reminding me.
I was just confused. Great.
You are completely reasonable. All right. Thank you. There it is. Can you see it now?
Yes, sir.
All right. So let's say that again, right? A set S is all these little teeny little cubes of size of Planck's constant cubed, and S is all of them that are in our universe. And we're going to count how many there are. Well, Planck's constant is 10 to the negative 35, which is little. And the quantum mechanics says that nothing can be smaller than that. And the width of the universe is really, really big, which is 10 to the 27 meters, right? So, you know, this is 1 followed by 27 zeros. So it's a big number. And if you'll say, well, how many Planck's constants across is it? Well, you just divide those. And then how many particles are in S? How many of these little cubes? Well, it's you cube this number, right? Because there are this many in this direction, in this direction, in this direction. So that's how many quantums there are. And we also could multiply it by the number of quantum points in time there are as well if we want. But anyway, this is a big set, right? But here's a question. Is this set finite?
Yes.
Yes, it's finite, all right? So this set is finite, and I would claim that any set that's bigger than this, right, is not really part of our reality, right? When you're talking about the set of all integers, well, that's just a mathematical concept that has no actual real meaning whatsoever. All right, so now let's move up to think about countable infinite. And we're not going to quite get there yet. Let's have S0 be the set of all binary strings that have exactly 5 characters. All right, so there's a binary string with 5 characters, and there's another one, and there's another one. How many of them are there? Well, there's 2 choices for the first bit, right? It could be a 0 or 1. And then the second bit could be a 0, 1. The third could be a 0 and 1, so forth, right? So 2 times 2 times 2, there are 2 to the 5 of these strings, which, right, isn't that many. But anyway, it's exponentially larger than the length of the string, right? Now, let S1 be the set of all binary strings alpha, where the length is arbitrarily long. Each string in this set can be as long as you want it to be, except each one must be finite length. All right, we can't have infinitely long strings here. Each string has some finite length. Everybody get this set? Right? And we might want to think, well, how big is this set? And, you know, to embarrass ourselves around this same sort of notation here, if these strings are of length 5 and we have 2 to the 5 of them, and these strings are arbitrarily long but finite, then we can kind of say the size of this set is 2 to the arbitrarily large but finite, right? Whatever that means, right? All right, let's hold off on this. We'll talk about the size of the set again in a minute. But to understand this set better, we're going to think of a large number of ways of thinking about it, right? So each binary string, we can take each binary string and think about how to interpret it. And you know, everything in your computer is a binary string, so we can interpret it in different ways. And the first way of thinking about this binary string is to interpret it as an integer. All right, so you take the string 101, that's a binary string. You think about it as an integer mod 2, and that happens to be 5. Everybody know about integers mod 2? Shanaz, you know about integers mod 2? Binary?
Yes, sir.
Excellent. All right, so this kind of gives us a one-to-one mapping between positive integers and strings, these binary strings, right? And so we can almost even say these sets are the same because there's this one-to-one mapping between them, right? And how many integers are there? Well, we have a word for that. The number of integers is called countably infinite. And what does that word mean? Well, as you can imagine, you can count them, right? How do you count? I point at you and I say 1, and I point at the next person and say 2. 1, 2, 3, 4. That's how I count. I make a mapping. If I want to count the number of objects in a set, then I map each of those objects to an integer, right? And that's how I count. So if I can map every string in this set, I'm kind of mapping it to an integer. And so then we'll say that the size of the set is countable, right? Does that make sense? It's infinite, right? I guess here's another point. Are there an infinite number of strings in this set? Yeah, there's definitely an infinite number of strings. Why? Because there are an infinite number of lengths to begin with, right? It could be of length 0 or 1 or 2 or 3 or 4 up to infinity, right? So there is an infinite number of lengths, so certainly an infinite number of strings. All right, everybody following this? Yeah. All right, so let's think about other ways to think of this binary string. You can take any 4 bits and interpret it as an ASCII character. So we could take some binary string that has 4 plus 4 plus 4 bits and interpret it as the word cat, right? So any binary string can be you can say, well, what is the ASCII form of it? Now, of course, there might be some characters in there that are kind of weird, but that's okay, right? We get, right? So another way of thinking about this set is the set of all finite strings of ASCII characters, right? Like cat. So here's another way to interpret it. Here, what do we have here? 3/4. It's just an ASCII string, right? 3 is an ASCII character, divide is an ASCII character, 4 is an ASCII character. So that is an ASCII string, right? And and this ASCII string happens to represent the fraction 3/4, right? So now there are ASCII strings that don't represent fractions, but that's just going to tell us that we have more ASCII strings than fractions, right? More or less, though, if we ignore the fact that some of them are the wrong format, then we can think of the same set S as being the set of all fractions, right? And what's amazing here, and I hope you kind of get it, is that is we're saying that the set of all fractions, how many fractions are there? We're saying that the number of fractions is equal to the number of ASCII characters, which is the number of fractions is equal to the number of integers. And that's sort of surprising, because if you think about a number line, you have 1 here and 2 here, right? There are an infinite number of fractions in between, right? So it feels like, in fact, any 2 points, you take any 2 points on the real line as close as you want them to be, there are an infinite number of fractions in between, right? So the fractions are very dense on this real line, right, on this number line. So you would think that they would be more fractions than there are integers. But here we just kind of proved that the number of fractions and the number of integers is the same, or at least that there are more integers, right? Because here there's some ASCII strings that don't describe fractions. So there you go. Everybody kind of buy that? All right, so here's another way we can interpret each string alpha, which is a binary string. We could think about it as description of a Turing machine, right? A Turing machine, one of the big things we required of it is that it has a finite description, and given an input, it's clear what it does, right? So here we can think about this set as the set of all Turing machines, right? Everybody kind of got this?
Sure. So there's kind of a one-to-one correspondence.
Yeah, more
By
or less
equality, you mean that, right? Not
right,
content-wise.
Yeah. Every
Okay.
string, every Turing machine is described by some binary string, right? Now you might argue some binary strings don't describe valid Turing machines, but let's ignore that. And if anything, it makes these sets smaller. And our goal is to prove that these sets they're infinite, but they still can be counted. The point is, all of these sets are the cardinal. We could ask how big are they, but Cantor, who came up with these things, instead of saying how big they are, he used the word, what is their cardinality? And cardinality is because then their cardinality is countably infinite. Right? Does that make sense?
Yes, sir, it does. Thanks.
All right. So now let's go over to uncountable sets that are bigger than the sets of integers, right? All right, now let S2 be the set of all binary strings where each of the binary strings has infinite length. And now I still say its length is countably infinite, right? Because you could count the digits in this string. You could go, there's the first digit, there's the second digit, third digit, fourth digit, right? Every digit in the string could eventually be counted, right? Now, actually, let me, in case I don't have this in a slide later, I think this is a very interesting point. If I counted the strings of this, the characters of the string, the digits, the bits, what I go 1, 2, 3, 4, 5. Will I ever get to all of the digits? No, because there are an infinite number of them, right? But what's true is for any one of them, I'll eventually get to it. It's like the integers. You name, if I go 1, 2, 3, 4, I'll never get to count all the integers. But given any particular integer, I'll eventually get to it. All right, people getting this? All right, so now what's the size of S2? Well, it's kind of 2 to the infinite now. And if we had more time and more enthusiasm, then I would show you how to prove that the number of reals is bigger than the number of integers. All right, but we won't spend too much time on that. All right, so now, how are we going to think about each of these infinitely long strings? Well, we can interpret each of them as a real number between 0 and 1. How do you do it? Is you just put a decimal place in front of them, right? Oh, here I have it. Here's an infinitely long binary string. I put a decimal place in the front, and suddenly it's a real number. And if you've never seen real decimal places, it works out to the same. This is the half place, quarter, 8, 16, right? So this number is a half plus a 16 plus whatever else we got there, right? So that's how we do, we can think about real numbers. So this set S2 can also be thought of as the set of all real numbers between 0 and 1, right? Does that make sense? And as I've said, we could prove that there are more reals than there are integers. And if people want to cover that, we certainly can cover that. Now, another way of thinking about this binary string, right? It's still just a binary string of infinite length. I can think of this alpha as being a function that takes in an integer and returns 0, 1. All right, how do we do that? Well, let's just label each of the bits of this binary string with 0, 1, 2, 3, 4, 5 up to, right? Every bit is labeled, every integer is labeling one of these bits. And then I can say, now what's f of 0, right? I need to define some function f. So f of 0 is, I say, what's the 0th bit? It's a 1. So f of 0 will be 1, right? And what's f of 1? Well, what's the 1th bit? It's 0. So f of 1 will be 0, right? F of 2 will be 0. F of 3 will be 1. F of 4 will be 0, right? So you can see this binary string of infinite length is going to tell me a function from the positive integers to 0, 1, right? And similarly, any function from the positive integers to 0, 1 will in turn give me a binary string, right? So that means there's a one-to-one mapping between them, right? And so here we can talk about S2 being the set of functions from integers to Boolean, right? Does that make sense? Right? Everybody good? You following this? You Woo, Shanaz?
Yeah.
Yeah. All right. So now let's think of another interpretation, right? Here we're looking at functions from integers to binaries, right? But we already saw there's a mapping between integers and finite strings, right? right? Remember the integers correspond to binary strings of finite length, and those binary string of finite length were mapped to ASCII strings, right? So here, all right, so here I guess are all various, I guess we're mapping, or sorry, I guess we're mapping from finite binary strings to yes, no, right? So it's just what we did before. Here, the string 0 is the 0, so we can say it connects to 1. The string 1, right here is the string 1, 1 is 3. Run 1 in binary is 3, so 3 is mapped to a 1, and 1 is the same as yes, right? But 1, 0, 0 is 4 in binary, so 4 is mapped to a 0, which gets a no, right? Does that make sense? Right? People can shake their heads. All right, so all 16 of you. All right, so now, right, so that's right. So that's now, since again, this is now a binary string, and what I thought we were doing before is we can map what's a language, right? We can add each of these purple finite binary strings, we can map it to, we can think about it as a string in some alphabet, right? The alphabet 0, 1, or the alphabet ASCII. And this function will tell us whether the string is in the language or not, right? So here the string 1, 1 will be in the language, while 1, 0, 0 won't be in the language. Right? Does that make sense? So here we can think of S2 as a language. What is a language? Each language is a string, is a set of finite strings, right? So how do you know if you know L and I give you a finite string and you want to know whether that string is in your language or not, how do you determine it? Well, that string might be, if the string is 1, 0, 0, then you think about 1, 0, 0 as an integer, and you look up the integer's bit, and if the integer is 0, then you say, no, it's not in the language. If the integer is 1, you say, yes, it is in the language. Right? Does that make sense? Yeah? Am I killing you guys, or are you just like, this is obvious?
Oh, this is understandable. This is fine.
Excellent.
Yeah.
Excellent. So here, these are all, can you guys, these sets are all in some ways equivalent, right? The size of them all is the same as the number of reals. And I haven't proved it to you, but you can trust me that there are more reals than there are integers, right? You give me any way of counting the reals, I can give you some real number that you haven't counted. All right. So, and what is an L, a language? Remember, L is just like a computational problem, right? There's some input to the computational problem, and you have to say yes or no, or maybe you have some more complex answer. Maybe you say, right, computational problem could input a bunch of, but the point is, the computational problem takes in a finite description of an input and returns the finite description of an output. And this is kind of arguing that then the number of computational problems is the same as all of these other things. Can you kind of buy that? All right, here's just summarizing it in a chart, right? So we have finite, the set of a set that's a finite side versus an integers versus the real, right? And now what's the length of every object, right? here we have every object is of length 5, each string is of length 5, then what's the size of the set of all strings of length 5 is 2 to the 5, right? Now the integers, what's true about the integers? Each integer, you give me any particular integer, it has finite length, right? It could be really, really long, but it's still finite length, right? So the integers all have, each integer has a nice finite description, right? But the set of integers has cardinality countably infinite, right? They're an infinite number of integers, but I can count them by going 1, 2, 3, 4, 5 the integers, right? Does that make sense? Now the reals, each real kind of requires an infinite description, right? A random real requires an infinite description. And then how many are there? How many reals are there? There's an uncountably infinite number of them, right? Does that make sense? All right. So now I'm going to, given you understand that and believe that, I'm going to prove to you whether or not there exists uncomputable computational problems, right? So in the 20s, Hilbert put out to the world, are there computational problems that have no algorithms, right? That can't be computed. And and we're going to prove it right here on this slide, all right? Here's the set of how many integers are there, right? How many fractions are there? How many reals are there, right? And we've kind of, what's true about here, each integer is described by a finite string, right? You give me any integers described by a finite string. Any fraction is described by a finite string, right? Most reals require an infinite string to describe them, all right? And so that tells us, that's why, because of this, we say we can do a mapping between these as we did, right? The number of integers is the same as the number of fractions. It's because we can do a bijection between these two sets, right? But here, we can argue that there are more reals than there are fractions. All right, do you buy that? All right, so now let's think about the set of all Turing machines, right? This is the set of all Turing machines, the set of all algorithms. Each algorithm, each Turing machine has a finite description, right? And so the number of algorithms is countable. It's the same as the number of integers, right? But how many computational problems are there, right? Right? Given a computational problem, for every input, you have to tell me what the required output is, right? So to describe to me a random computational problem, you need to tell me for every input, the output will be some random thing. You have to tell me what it is. So the computational problem will require an infinite description, right? Does that make sense? And because each object in the set, or at least most of them, require infinite descriptions, the number of objects in the set, the number of computational problems is uncountable, right? And what does that mean? That means that there are more computational problems than there are algorithms. And that tells me that most computational problems, if you took a random computational problem, it does not have an algorithm, right? So this is saying there exists a computational problem. If you're all up on first order logic, certainly Shanaz is, right? There exists a computational problem, right? Such that you give me any Turing machine, I give you a computational problem, such that you give me any Turing machine hoping to solve this computational problem, and I'm going to give you some input, on which the computational problem, the Turing machine gives the wrong answer for the problem, right? Does that make sense? All right. Everybody kind of follow that? So you might have seen the slides already because you were supposed to watch them before now. These are my brand new slides that you've never seen, and I think they're fun. So in some ways it's new material I'm putting into this course, but I think it's fun. All right, so here are 4 binary strings of length n, right? In some really, really, really big number. Here's our 4 binary strings, all right? And my question is, we're gonna keep, this is a repeated question. I'm gonna keep asking this question. Which of these strings is more random, right? And so my first kind of answer to the question, which is more random, is going to be to know how they were produced, all right? So how did I get this first string? Well, you'll notice it has a pattern. It goes 1 0 1 0 1 0 1 0 1 0, right? It has a pattern to it. The second string here, the way I got it is I asked Google what pi was, and it said it was 3.14 right? And then I asked Google to convert that into binary. And this is the binary representation of pi. You'll note it starts with 1 1, which is 3, right? 2 plus 1 is 3, right? So that's what pi is. This one down here, the way I generated it is for each bit, I flip a fair coin, right? And how did I generate this one? Well, I flipped the coin for each bit, but it wasn't completely fair, right? In fact, what I'll tell you, a property of the string here is that the number of zeros is slightly less than half, right? In a random string that was really, really, really long, you would expect that the number of zeros was pretty close to half, right? And this one, it's the number of zeros is going to be exactly equal to 0.49n. All right, everybody got how we got these 4 strings?
Sir, what do you mean fair coin, unfair coin?
Oh, a fair coin is that when you flip it, the probability it gets heads is 50%, right? And an unfair coin is, it's slightly more likely to get a heads than a tail.
All right, yeah.
Right?
Yeah.
The probability of a tail was 0.49, and the probability of a head was 0.51, right? So it was a biased coin, right? Does that make sense? Right? If you are playing dice with the gang down in your block, they might kill you if they figured out that you were playing with unfair dice, right? All right, so now we can ask which one is more random, and what do you feel about it? Is the first one random? No. This one here, it's the definition of random, right? I produced it by flipping coins. And this one's almost random, but not quite random. This one's definitely not random. It has a pattern. What about this one? Is it random?
Yeah, yes.
We could say there's no pattern to it. So we could say it was random, right? We could say that, right? Certainly, if I told you the first billion bits, you would have a hard time telling me what the next bit was, right? All right, so let's ask the question again. Which one's more random? But this time, let's say if I were to flip a coin n times, what's the probability that I get this string, right? what's the probability I get this string or this string or this string, right? Anybody know? Right? Well, the first time to get this string, there's a 50% chance that I get a heads the first time, and then 50 that I get a tail, then 50% I get a head, and 50% I get a tail, right? So that's 2 times 2. It's right. The probability I get this, exactly this string, is 1 over 2 to the n. Right? Everybody agree with that? And that's the same for all of these strings, right? They're all equally likely if I were to flip coins. So we might argue that they're all equally random, right? They all have the same probability. You could say, oh, well, what's the probability of getting this string? Well, it's pretty small, but the probability of getting this string is equally small, right? They're exactly the same. Right? Everybody get that? All right, so let's ask another question. Again, which one's more random? And we can ask which one has a short description, right? So if you're going to just describe it to me in English, which one has a short description, right? So this first one, I just say, hey, it alternates between 0 and 1s. I guess I got to tell you how long it is. I guess I have to tell you that it starts with a 1, right? The second one has a very short description, right? It's called pi. Maybe I have to say pi in binary, right? But it's still a short description. This guy here, how could I describe it? If I needed to tell you the string, right? How would I describe it, right? Well, you could be smart aleck to me if you wanted, and you could say, well, this exact string, I'm going to call it Bob's string. So now it has a short description, right? That's Bob's string. All right. Somehow it feels like cheating, but let's come back to that, right? Now, here I'm going to ask, how many descriptions are there of length with n-1 bits, right? Let's just count. Let's say a description is, right, it's basically a binary string, right? If this is an ASCII string, and I convert that string into binary, right? So basically I'm describing this binary string with this binary string, right? And so I could ask, how many descriptions are there that are only n-1 bits long, right? Well, how many how many strings of 0s and 1s are there that have n-1 bits? That's many of them, right? 2 to the n-1. Everybody know that, right? Because there's 2 choices for the first bit and the second bit and the third bit, right? That's how many descriptions there are that have this length, right? So what can we say? How many binary strings of length n are there? There are 2 to the n of them, right? There are 2 to the n strings like this. So what can we conclude here? We conclude that half of these strings need at least n bits, right? If I chose this string randomly, then with probability a half, it's going to need at least n bits to describe it, right? So to say that this one is called Bob's string is a bit of a cheat, right? Another way of thinking about this is a communication complexity, right? Suppose Bob flipped all these infinite number of coins and Bob knew this string and he needed to send me bits to tell me what the string is. And we could have any communication method whatsoever, right? In order for him to tell me in random bits, he really does need to send me the bits, right? He has to send me in bits to tell me in bits. That's just a law of communication complexity, right? Does that make sense? Right? So we can say which one's more random. We can say based on, right? So back here, I guess, this one's not so random because it has a finite description, right? And this one's random because it seems to need an infinite description, right? Now, this whole idea of a description, what's a valid description and what's not, right? People could get worked up about, well, what language? Are we doing this in English? Are we doing it in Chinese? Are we doing it in ASCII? How are we interpreting these descriptions, right? Who told you that this symbol was pi, right? It relies on some previous knowledge. And we want to get away from that idea, right? So in order to get away from this, I'm going to ask a new question about which one's more random. I'm going to say, which one can be outputted by a Java program with a short description, all right? So the way we're going to get these strings is you're going to give me a Java program that has a shortest description possible. And that Java program, we're going to run it on no input. You just run it without an input, and it's going to start spewing out digits, right? It's going to start spewing out bits. And because the string is infinitely long, right? We will never, oh no, actually it's only of length n. Sorry, if it was infinitely long, it would never stop. So, but it could spew out all the bits. But our string is of length n, so it eventually will spew out bits and eventually stop, right? And we're going to describe the complexity of this string as the length of the shortest Java program that outputs it, right? And that's called Kolmog complexity. This guy was some Russian, all right? That's why he has a name that sounds like that, all right? Does that make sense? People get this definition here? All right. So again, we can say the same thing. How many computer programs, how many Java programs can be described by n-1 bits, right? Well, only 2 to the n-1 of them, right? Because there are only 2 to the n-1 strings with n-1 bits, right? So what does that tell us? That, well, they're 2 to the n of these strings, and so half of these strings require programs whose length whose the Java program is at least length n, right? Does that make sense? Are people kind of following this? Right?
Yes, sir.
Right, so here's a Java program that's outputting this, right? It's pretty short. Here, Newton could give you a Java program that could output all the bits of pi, right? Here, these were all flipped randomly, right? When I flipped them randomly, you could do a little math here to prove this. What's the probability I get a string that can be described with n-k bits, right? You can always describe a string with n bits, right? You just say print, and then you give me the string, right? So it's slightly more than n bits because you have to count the word print, right? So every string can be written with n+5 bits by just saying print the string, right? But can it be described by n-k bits? You know, is there a Java program with n-k bits that can output it? And the probability that happens, right, is exponentially close to 1, right? That it needs at least this many bits, right? So almost for sure, you're going to need all full n, almost n bits, right? Now, here we flipped an unfair coin, right? And we could ask, so this is what I was up canoeing, and I was asking the question, right? How big of a Java program do I need to output the string, right? And And so that's what we're going to talk about now. Is we're going to focus on writing a Java program that will output the string. And here, let me first tell you something about it. Right, this is a string that has the property that the number of zeros is exactly 0.49 in, right? So I could ask how many strings have this many zeros? And the answer is, right, I rounded things a bit, but more or less this is the number of such strings, right? Here, this number is, right? So you'll see what you should know about 0.99997 is that it's slightly less than 1, right? Because the number of binary strings is 2 to the n, 2 to the 1 times n, right? And this is slightly less, right? Now, you might ask, where did I get this number from? And we won't go into the math of why this is the case, but let me tell you how I computed this number, right? This function h is called the entropy function. Shannon's entropy, which we could learn more about entropy. It's a great subject. But basically, h takes in a number between 0 and 1, and it does this calculation. And if you put in 0.49, it comes out with this number. So that's how I got from this number to this number. All right. And so now what I'm going to prove to you is that there is a computer program that has this many bits in it, that's described by this many bits, and it outputs any one of these, right? For any string with this property, I can give you a Java program that only has this many bits, and it outputs your favorite string, right? And that kind of tells me that these strings aren't quite random, right? Because they have shorter descriptions, right? Instead of the description, most strings need descriptions of length n, right? But this one requires description that's slightly smaller, right? Does that make sense? This particular string is less random because it can be described by a small Java program, right? Usually we think about randomness as a distribution, but here we're going to talk about it. It's sort of random because it has a short description. All right, so which one is more random? Well, these are very patterned because they have very short Java programs. And this one's completely random. And this one, hello, mother, I'm trying to hang up on you. There, I just hung up on my mother. And this one is not quite so random, right? Because it has a shorter description, right? Does that make sense? Is everybody following this? All right. Now, let's just point out that we're not caring about running time here at all, right? We're just all we care about is, does it output the right string, and what's the length of its description, right? And let me tell you, I have to hang up on my mother again. What are we saying? So why am I teaching you this? Well, one, I think it's cool, and two, computer science is all about describing things, right? Having descriptions. So I do think it's kind of relevant to computer science, right? All we're talking about is the information. How much information is in the description of the Java program, and how we translate that over to the information of the string that we're outputting. All right. So how does this relate to entropy? Suppose you took your room and you cut your room built in half, right? So there's this half of the room and that half of the room. Mother, hey, Mom, you really got to stop calling me. I'm in the middle of a class. This is my room, and suppose you counted the number of particles and there were slightly fewer particles on one side than the other, right? Then it would not be, this wouldn't be considered random, right? We would say that the entropy was low, right? You know, one thing about so some guy came up with the definition of thermodynamics entropy, and they kind of argued that entropy always increases in the universe. And this is what he meant about it, is if you had the system, entropy of the system would increase. How is particles would fly back and forth, and then you would have the same number of particles on both sides, right? Everybody follow that? So now, how would thermodynamics define entropy? Well, they have a sense of a microstate and a macro state, right? So the microstate tells me, it tells me the position of every, maybe it uses a binary string, right? The microstate uses some binary string to describe the position and velocity of every particle. All right, so that's the micro, right? You get right down to the little bits and you tell me the microstate. And what's the macro state? Macro state is you can just observe it. Maybe I'm observing the pressure on this side versus the pressure on this side. I'm observing that in a macro sense, there's a higher pressure on one side of the room than on the other side of the room, right? That's our macro state, right? And so our property is going to be there are more particles on one side than on the other side, right? And then thermodynamics entropy, what does it define entropy to be? Is you let in, given that your thing has its macro state, how many microstates are there equivalent to it? And you take the log of that to get the entropy, right? So that's thermodynamics entropy, right? And you see, you're taking the log of it, is that's because you're having a description. If you have capital N objects, then each of them can have a description of length log n. But the guy who came up with this definition didn't know about information. We had to wait for Shannon to talk about information. Anyway, then we also talked about chromographic clause complexity of a string, right? Is the minimum number of bits to describe a Java program that outputs the string, right? So now we can talk about the Chromov complexity of a macro property, right? What's a macro property? Remember, is saying, hey, I have 0.51 in particles on this side, and I have 0.49 particles on this side. That's a property of the string. So the Chromov complexity of that property is, if I gave you a string, what's the length of the shortest Java program that can identify, will tell you whether it has the property or not, right? So this is kind of tells you how complex the macro property is, and this tells you how complex the micro property is. Anyway, here's a theorem that I proved. I'm sure somebody proved it before, is that these definitions are all related, right? So these numbers are really small, right? So it doesn't take a big program to count the number of ones and see if it has exactly 0.49 in zeros. So these take small Java programs. And then that tells me my chromographic complexity is about the same as my thermodynamics definition, right? Right, and what's cool about this is that it tells you if your universe is in a low entropy state, then no matter what that state is, it's just one location of the particles, right? We can talk about one location of the particles, and we can talk about that it's in a low entropy state because I can describe the location of all the particles with the smaller Java program, right? You don't have to be thinking about the set of all possible states. You can talk about one state of where are my particles, and if I can describe that with a small Java program, then the entropy is low. All right. And maybe this has all gotten longer than I hoped it will, but we can finish in a couple more slides. All right. So our microstate, remember, is some binary string of length n. Our macro property is that the number of zeros is exactly this, right? In capital N is the number of strings of length n that have this property, right? And so let's think about it. Let S sub Cn be the set of all binary strings of length n with exactly Cn zeros. All right. And so then we want to know how big is the set, right? It's the choose. If you might remember choose, right, is I have a string of length n. How many ways are there to choose where to put Cn of the bits, right? Because I want C of the n of the bits to be 0. So I have to choose those those Cn spots to put the zeros. And this is a bell curve you've seen before, right? Most of strings are 50-50, zeros and ones, right? And then you go over 1 standard deviation, 2 standard deviations, 3 standard deviations. The size of the set goes down really quickly. All right. So as I've sort of hinted before, one approximation of the size of the set uses this H function. Here's a plot of the H function, right? And you'll note that if C is a half, right? So here we're C and a half. So H of C is 1. And the number of strings 50-50 is pretty close to 2 to the 1 n, right? Now, if C is 0.49, then we're shifting over slightly, and the number of such strings is smaller. And if C is 0, how many strings are there that have 0 zeros? Well, there's only one string of 0 that has 0 zeros. It's the string that has all ones, right? So that's why if C is 0 or C is 1, right, we get H of 0 and H of 1 are both 0. And that's because we're of this. Everybody kind of follow this? Anyway, we're focused on this right here. We have let S be the set of all strings that have exactly 0.49 n zeros in them, right? And that's how many there are. And the entropy of that is you take the log of this number, base 2, right? And the log of this base 2 is just that top bit, right? And you'll see that the number of these is right, the entropy is less than n. Are people good here? Are you following this? Yeah. Shanaz, you're back. Were you following it, but just camera off?
Yes, I was just having my tea, so.
Oh, well, we can watch you drink tea.
Okay, thanks.
All right, so here, now let's understand this a little bit better. What have I got that listed here? I've listed all binary strings with n bits that have exactly 0.49 n zeros. See, this one has this distance is 0.49 n, right? And I've listed all, and here over here we have 0.49 n zeros, and this is all strings of that have that property, right? That's my set S. And how many of them? There's this many of them, right? over here, I'm going to label, I'm going to put down what betas, which I called labels, right? And this is going to be all strings whose length is 0.9997 in, right? And here I just put them alphabetically, right? 0, 1, 2, 3, alphabetically, or ordered by cardinality, right? Here they are ordered, right? And how many of them are, there's the same number, right? So that gives me a mapping from these strings to these strings, right? Does that make sense? So each string here kind of has a smaller description, right? So this string is of length n, but it has a description that's slightly shorter, right? These strings aren't completely random because each of them has a shorter description, right? Does that make sense? Right? So this is a crazy mapping, right? It's a crazy mapping. Now I'm asking, can I write a Java program that will compute this mapping? It's going to take as input beta, and it's going to output the corresponding alpha. All right. So I'm going to write this Java program. All right. So because remember, we want to say that each of these strings here has a small Kolmogorov complexity, right? Meaning they have a short Java program. So I'm going to write a Java program that's going to output any one of these strings, and its length, the length of the Java program is going to require this length description. All right. So let's start with a Java program, which given alpha tells you whether or not it has the macro property, right? So what does that mean? You give me a string, any string alpha, it returns yes if the string is a binary string of the length n that has exactly 0.49 in zeros, right? Can you write the program like this, right? It just counts the number of zeros, counts the length, checks that it's all binary, it says yes, right? It has a very short description, right? Now, here's another Java program. You put as input one of these, the ith binary string in this list, and what it outputs is the ith plus first binary string in this list, right? It just gives you the next one. Anybody can think about how to how to write such a program? Here it is. Here's the code for it. I'm going to think now, these are binary strings, right? But remember I told you, you can think of a binary string as an integer. So I add 1 to it, right? I just take the binary string I have, I add 1 to it, and now I have a new string. And I ask, does that new string, oh, I guess there should be a sub I here. Oops. Does that new string have my property? And if it has the property, I return it. If it doesn't have the property, I go to the next binary string. And if it has the property, I return it, right? So I'm going through these strings, right? These strings are in order in terms of their integer value. So I keep going to the next integer, until I get one that has the right number of zeros, that has the property. Does that make sense? So it just gives me the next string. All right, so now here's a program which you give it beta and it outputs alpha. How does that one go? Well, it starts off with basically the 0 string, and then it keeps asking, it counts. It goes, give me the next string, give me the next string, give me the next string. Every time it gets the next string, it counts, and it counts up the beta. And when it counts to the beta one, it prints out the string, right? And so here it's counting these, and it will return that string, right? So this program, do everybody see how this program, here's a program, and it prints out our favorite string, right? Taking any string here, alpha, here's a program that outputs that string alpha, right? And the running time might be horrific, but we don't care, right? What we care about is how many bits does it take to describe this program? And how many bits? Well, it's the number of bits to describe this program. Well, first there's how many bits in this. Well, that's just maybe it takes 1,000 bits to describe that. And how many bits does it describe to take for this piece? Well, that's pretty short code. We can get that into the 1,000. What about the code for this, right? That's the Kamar complexity of the property, right? And now what's remaining here? What haven't I counted in our description of this code? Anybody guess? It's the beta, right? Somewhere I have to get the beta into the program. And how many bits does the beta have, right? The beta is the thermodynamics. It's the definition of it's the log of the number of possible strings in S, right? And that completes our proof. And so what's the point here is that this thermodynamics measure of this one string somehow tells me how random the string is. And this just says we can go the other direction. Yeah, that's not worried about. We're getting too weird here. That's it for that. Any other questions?